Hello, my name is Erica Tuttle, and I'm going to introduce today's lecture. Thank you for joining us today for the Clean Energy Project 2011 Earth Day webcast. Today's lecture will take about 12 to 15 minutes, followed by a question and answer session. If you have a question that you wish to ask, then please go to the chat interface on the right side of your Lotus Live window, type your message, and then press send. This lecture is being recorded and will be available for playback on our website. At this time, please welcome Victor Burstis, an IBM employee who has been one of the leading members of World Community Grid since before it was launched in 2004.
Hello, my name is Victor Burstis, and I'm on the technical team at worldcommunitygrid.org, which lets computers perform humanitarian research during their spare time while they would otherwise be consuming electrical power, just waiting for that next keystroke or mouse movement. One of the research projects on World Community Grid is the Clean Energy Project from Harvard University in Cambridge, Massachusetts. They've been running their research on World Community Grid for a little over 2 years now and are in the second phase of their research, searching for less expensive and more efficient materials to harness the sun's energy. Please let me introduce Dr. Alan Espuru-Guzik from Harvard, who will tell you about the purpose and science behind the Clean Energy Project running on worldcommunitygrid.org.
Hello, everybody. Thank you, Erica. Thank you, Victor. It is really a pleasure to be able to address you guys through this medium. I am here with some of my team members, Roberto, Shule, and Johannes, which regularly update to you in the forums. So please go to the forums and see, because almost every day we tell you what's going on with the project. So as Victor was telling you, our project is about to try to find out flexible organic solar cells. So our research group concentrates on organic photovoltaics and photosynthesis, as well as quantum computation and electronic structure. But today we're going to be talking about organic photovoltaics. And just to get an idea about the size and magnitude of the Clean Energy Project, I wanted to show you who really did the work in our team. Here is the name of the people in the Harvard team, which are the ones that do the theory. That's the first row. In the second row, we have the Stanford and IBM teams, the pictures of them. And then in the last row, we have the QChem team. QChem is the software that we use in your computers. IBM, of course, are the people that enable this to work on the grid. And the Stanford team is the team that actually makes the molecules that we are predicting using your donated computer time. So let's think about organic photovoltaics. These materials are actually already in production. For example, a company called Konarka here in Massachusetts already produces these materials here in the right. And in the left, you can see, for example, a nice application. You could have a flexible organic photovoltaic device in your purse that charges an iPhone, for example. So many applications that involve flexibility and cheap materials are the ones that actually we're after. So if you actually look at the next slide over here, what actually you can see is the efficiency of different types of photovoltaic technologies. For example, in this line over here, we see, in this green in general, we see silicon. So all of these guys over here are silicon. What we're after in this project is actually thinking about this line over here, which is the line of the organic materials. So the organic materials are very promising because, as you can see, in the last 5 years, we have been able to take them as a community up to 8%. And the goal of this project is actually take us up more or less to the area where silicon is, in the fastest amount of time possible, and that's where we need your computer time. So how do organic photovoltaics work? Organic photovoltaics work by absorbing in a certain molecular layer, say this molecular layer, which we call the donor layer, absorbing light and creating an electron-hole pair that we call an exciton or an excitation. So it's basically this guy over here. Okay, this is the electron-hole pair. That basically, this difference of energy between these two levels is called the gap, okay, between this level, and this is called the highest occupied molecular orbital, and this is called the lowest unoccupied molecular orbital. This excitation migrates to an interface where it's accepted by a donor layer. And there's many processes like exciton formation, diffusion, separation, followed by charge transfer and ejection on the electrodes that we have to optimize. In the Clean Energy Project, we're actually at the beginning of the project in phase two, we're actually working on exciton formation and exciton diffusion and a little bit about charge transport. Okay, so these are kind of like the areas in which our group is actually working on using your computer. So now, if you're actually targeting high-level, high-efficiency materials, you can actually tune those energy levels I was showing you in the slide before. Okay, you can actually tune them, and as a function of one of the parameters, which is the gap, the difference in energy that I was pointing out, and one of the levels, the level of the lowest unoccupied molecular orbital, you can actually see, based on this research by Sharber, that there is an area that we kind of like to call it the green target, which I drew here as a green target over here, in which you can actually end up with a 10% solar cell, which will be commercially viable. Most of the materials that people produce right now are around here, 5-6% efficient, the good ones. So the question is how to get from here to here in a reasonable amount of time, and this is where your computers are helping us. So I'll be showing you later plots like this, in which we have this LUMO level and this band gap level, okay, which are the ones that we're trying to tune using your computer time. Okay, so the question that we want to ask is, what is the best molecule? Maybe members in the audience might say, okay, perhaps I think that this is the best molecule, and as a matter of fact, pentacene has been one of the nice molecules for organic electronics, for example. Or somebody might say, well, an organic chemist might say, this is this molecule. And of course, one of the molecules actually that our group predicted is this molecule. Okay, it's been synthesized and characterized at Stanford. But the point here is that it's very hard to find out pre facto what is the best molecule. So the first option is to do experiments, but it takes about a year or so for experimentalists to synthesize and characterize a molecule, perhaps half a year if you're very good. The second option is to actually take some of the people that run the screensaver. Here we have a picture of Roberto, Schule, and Johannes, which are here. So now you know how they look like. So if you were to have Roberto, Schule, and Johannes study a molecule by themselves, okay, so by each one of them, then basically it will take a lot of time. Let's say, for example, perhaps they could study a molecule a month with a computer. Option number 3 is to learn what people do when they actually use distributed computing. And of course, the first project here was, for example, SETI at home. If you give people a nice way of actually participating, many people have contributed to this idea of searching for extraterrestrial intelligence, so we want to learn from them to design new materials. And this is what we did, and that's what we're working with IBM. So this is a project in which, in a partnership with IBM, has allowed us to deliver to you a safe and nice, beautiful client. What you see over here, if you have wondered what you're actually seeing, this stuff over here is actually the quantum mechanical matrix that is being diagonalized step by step, and the more higher the peaks here, the better your calculation is going. And whenever the peaks are very high, then the calculation is done. We actually have the computational power that is listed down there. And of course, you can download it before. Probably all of you already have it. But remember to tell your family to download this. This is very important. Okay? So anyway, this is the client that you're actually using in the World Community Grid. The amazing thing is that we can scan 10 to 20,000 compounds a day. So if you think about it, we're about 20,000 times faster at best than a theoretician that could do perhaps one a day, and 200,000 times faster, or even 2 million times faster than an experimentalist. Okay, so this is the reason why this is so exciting, because we can really scan molecules really fast. Okay, so this project really tries to do tight integration with experiment. What we're really trying to do is whenever we produce a prediction for a molecule that is really good. And of course, we have to be very safe that this molecule is actually a good molecule, because it takes a long time to synthesize. We call our friends at Stanford and tell them, can you please start working on this molecule? Now we're starting to work with other groups around the world to send them different types of molecules, to have many people busy with predictions from the screensaver. After that, we characterize them, which also takes a lot of time, and then we feed those back into theory. This is actually one of the first feedback happened 2 days ago. I was at Stanford getting feedback from the users. Okay? Sorry, from the group of Shenan Bao. Okay, so that's kind of how this works. And the idea is to actually do combinatorial chemistry. So this is kind of like the bird's eye view of the clean energy project. What you see in green is what we already have finished, and what you will see in yellow in the next slide is what we are actually working on, or almost finished. So the project starts here. The Bao group gave us 26 molecular fragments that we combinatorially devised into about millions of molecules. Let's say about 3 million in our first library, but we are actually growing the library as we speak. For example, perhaps we will be adding very soon 200,000 new molecules. From that, we actually go and using QChem, this yellow area over here, that probably you cannot read very well, but this one over here is actually what you guys are helping us do via the cyber infrastructure of the World Community Grid. That is going on into a database that we finished developing and we're populating. We do cheminformatics, structure property relationships, and then we actually then send back stuff to the Shenandoah that actually closes the cycle. Okay? And this is happening as we speak, and whenever we are busy and we want what we're doing, this is what we're doing every day. Okay? So now, these are the 26 building blocks. If you wonder what the building blocks, what we want to do is actually combine them with the computer in many different ways to actually build up the actual materials. We build three-dimensional structures out of them, and then what we want to show you right now is how we actually the results from the project. Okay, because so this is just for the jokes here that know quantum chemistry. Okay, if anybody knows quantum chemistry, these are the methods that we're running in your computer. All the stuff that you see in this slide is what's being computed. And offset for the people that are not technical, this is basically what we're doing in your computer if you wonder what calculations are going on. But these are actually finally the results. Over 1.5 million molecules have been computed by you guys, by you all. Here is the number of the distribution of the number of heavy atoms, basically how big the molecules are, and how many electrons do they have. Okay, so this is just an example. This is the first time in history probably that somebody shows you a plot where you have a bar that has 200,000 molecules. Okay, so this is thank you to you guys. These plots are first time in history that one can actually do so many quantum calculations on a set of molecules. Okay. For example, now here are the trends and energetics on the energy levels of the highest occupied molecular orbital. Okay. So what you can actually see in this plot, they are slightly technical, is that actually some of those different levels of theory give us different levels for the highest occupied molecular orbital, and you see them here as slightly different colored curves over here. Okay, we can then calibrate to experiment, and as you can see, when after we calibrate to experiment, all of them lie in the same area. Okay, and what we can actually now do then, and actually this is the last slide I will be showing you here about results. We can actually look at at those molecules in this Sharper plot, and remember, we were after this area over here, the 10% area. Well, guess what? We do have about 5,000, that's the underestimate. I heard this morning we actually is more about 25,000 to 50,000 molecules already out of our database that live in this 10,000, 10% area. This is where we actually can change organic photovoltaics. If the molecules from here are actually characterized and measured to be 10% efficient, I'm coloring it with another color just to remind you that area. That's the area that we're going to actually start sending molecules to the experimentalists in the next coming months. Okay? But the problem is that if an experimentalist was able to try to find this at random, it will be, let's say, less than 1,000 chance of synthesizing a molecule. So perhaps it will take them 1,000 years to do this. So with that, I want to end showing you that we can also compute other molecular properties. But in general, finally, because I am running out of time, but I just want to show you some of the molecules we predicted. Randomly fishing from those, 30,000 molecules, you can see some of the oligomers that will build the polymers for the next generation of organic solar cells. Okay, we're sending some of these to experimentalists very soon, okay, to try to make them. Here is the picture of the Clean Energy Project teams, some of us, now you see our faces, Schuller, Roberto, Carlos, etc. And this gives you an idea of the Harvard side of things, but of course, as I showed you before, the IBM team and the Stanford team are essential to this project. I want to thank you and open up for questions.
Thank you, Alan, for a very informative talk about the Clean Energy Project running on worldcommunitygrid.org. To those listening today, thank you for attending the webcast. We hope you have learned more about this project and will continue to contribute your spare computing power and also encourage your friends to join worldcommunitygrid.org. The question-answer session will follow in part 2 of the webcast.